forward biased PN junction. How you are going to forward bias a PN junction is that with a semiconductor diode, which is having let's say a p-type region and an adjacent n-type region. So we have a p-type region and we have an n-type region. How you're going to connect this with an external battery is that the terminals p-type is going to connect to the positive terminal of the battery, and the negative terminal of the battery, the external bias, is connected to the n-type region of the semiconductor. What happens is that when there is no bias, you have a depletion region across the junction. This is a PN junction, okay. And in this PN junction, there is a field that exists that stops the diffusion process of majority carriers. For example, from P-type, the whole carriers, it halts the holes from diffusing from P-type to N-type. Similarly, electrons, they halt from moving from diffusing from N-doped region to P-doped regions. Okay, so if you apply a positive, if you forward bias a junction with such polarity, what happens is that you narrow down the depletion bit. The net electric field is decreased. Okay, owing to that, if the net electric field is decreased, and you must notice that the net electric field is still in the direction it's from N to P directed. Okay, and let's say the external battery VD is small, which is less than the barrier potential VBI. VBI is the potential due to the electric field establishment from N to P type, from N to P side. Reason being because you are uncovering the ions. On the N type you have positive ions, on the P type you have negative ions, and that's why the electric field is directed from positive to negative. So it's N to P. So okay, so let me draw this ions. So we have positive over here. Okay, these are trivalent impurities, and then we have negative, for example, boron or any trivalent impurities. So you see, it's not like that is from negative to positive. It's because the ion charges are distributed as such across the junction. That is from positive to negative. Okay, this resulting electric field, which holds back the diffusion of holes from P-type to N-type region and vice versa, is decreased. This net electric field is decreased owing to the external bias VD, and that happens to forward bias the PN junction so that the carriers, the equilibrium, the delicate equilibrium, when it is disturbed, there's going to be diffusion from P-type to N-type region. So there will be holes that are going to flow from P to N-type regions, and then there will be another diffusion of electrons. There will be electron negatively charged particles from N-type to P-type. Now you notice that the electrons, they will be minority carriers in P-type region. Similarly, holes from the majority P-type to N-type will be minority carriers, and then there will be some recombinations. So you will get back the steady state equilibrium back, and the concentrations will start to drop to the thermal equilibrium values. So this across the junction, there will be a net current, okay, because of the flow of charges. So this is the story. So now we have seen that the N region contains more free electrons than the P, and similarly P region contains more holes than the N region. So with zero applied voltage, built-in potential barrier potential prevents these majority carriers from diffusing across the space charge region. So the barrier maintains the equilibrium between carrier distribution on either side. So initially, without any bias, when there is no external bias, you have the barrier potential, okay, VBI, and that is not allowing any diffusion of charges. There is no current across the junction. So if a positive voltage VD is applied to the P region, okay, so positive is connected to the P region, the potential barrier decreases. This is shown in figure 1.15. So this is what is going on in here. Positive is connected to the P-type region, and then you have negative connected to the N-type region. So what happens is that the electric field due to the applied battery is EA over here, and the net electric field is decreasing. Net electric field, which is due to the uncovered ions on either side, decreases. Okay, so the depletion bit, in fact, decreases. Okay, so the electric field in the space charge region is very large compared to the remainder of P and N regions because of the uncovering of ions primarily. You have uncovering of ions, so in the remainder of NP regions, there is not much field. So essentially, all of the applied voltage exists across the PN junction. The applied electric field, EA, induced by the applied voltage is in the opposite direction of the thermal equilibrium space charge E field. However, the net electric field is always from N to P region, as can be noticed over here, right? So the direction of the net E field is always from N to P, and that is due to the uncovering of ions, okay? And you must also notice that VD is a small positive voltage, less than the barrier potential VBI for now. So there's not much current that is going, you can expect to flow across the junction, but this does results establishing of EA field. It does disturbs the balance, thermal equilibrium, and does supports the flow of charge. So you're going to expect some current in the PN junction, okay, or at this metallurgical junction x equal to 0, let's say. So at the interface there will be some diffusion, but then this diffusion, for example, holes which are going from P region to N region will be minority carriers. They will be recombined with electrons, and you're going to get with a steady equilibrium back. Steady state equilibrium back. So similarly, there will be some minority carriers electrons which are going to flow from the other side, okay, and they will recombine with the holes. So there will be some excess of minority carriers across the junction, okay, but it's going to the concentration is going to drop. So the net result is that electric field in the space charge region is lower than the equilibrium value, okay. Now this upsets the delicate balance between diffusion and the E field force. So majority carrier electrons from the N region now start diffusing into the P region, and the majority carrier holes from the P region diffuse into the N region. So this process continues as long as the voltage VD is applied, thus creating a current in the PN junction. So this current is due to the minority carriers on the other side now. So this diffusing into the P and N regions. So this process would be analogous to lowering a dam wall. For example, if the dam wall is lowered, there is a large flow of water, okay, so a slight drop in a wall height can send a large amount of water or current over the barrier. It's just like that. So we are just lowering the barrier potential. So the depletion width of the space free charge region is decreasing, so you're just lowering the barrier in order to allow the flow of charges across the interface. So the applied voltage polarity is known as a forward bias, and forward bias voltage must always be less than the built-in potential. So what's going on over here is, you see, as a result of this disturbance in the balance, in the equilibrium, holes start to flow, diffuse across the junction, and they start flowing from P region to N region. Similarly, from N to P, we have another diffusion of electrons to which are the majority carriers in the N-type region to P-type region. And you see over here, the concentration is of the minority carriers. The minority carriers are holes over here. And then you have the negative, which are the minority carriers in the P-type region. Okay, although they are majority in the other regions, for example, the holes are the majority carrier in the P-type, and in the N-type you have the electron. So what goes on is that as they travel across the adjacent N and P-type regions, the excess electron concentration, for example, in P-type region, this is the excess electron concentration, it falls off, right? Because of the recombination with the majority carriers, which are the holes. So electrons are going to be recombined with the holes, which are in majority over here, right? Holes are in majority. So they're going to recombine with these minorities, and similarly electrons which are in majority are going to recombine with the holes which have come across the the junction. So the excess hole concentration and the excess electron concentration on both sides is going to reduce to the steady state value, okay, NP naught and PM naught, okay. So this is the process which is going to happen when you forward bias the junction by application of an external bias, VD. So the steady state minority carrier concentrations in a PN junction and a forward bias is shown in figure 1.16, and the gradients in the minority carrier concentration generates diffusion currents in the device. So as the majority carriers, they cross into the opposite region, they become minority carriers in those regions, causing minority carrier concentrations to increase. So you see at the interface the concentration has increased, but then after the interface along the x-axis on either side, positive and negative, the concentration of the minority carriers is decreasing. Figure 1.16 shows the excess minority carrier concentration at the space charge region edges, and then these excess minority carriers, they diffuse into the neutral PNN region where they recombine with the majority carriers, thus establishing a steady state condition as shown in figure 1.16. So it's not like because of the diffusion of holes and electrons across the junction, you have the excess, you're increasing the minority carriers. Well, they are recombining and you're getting back the steady state values of the concentration back. And this is happening when your forward biased VD is less than the barrier potential. Okay. I mean, this application of VD basically is, you understand that it disturbs the equilibrium and helps the diffusion process of the charge carriers in both from p-type to n-type region, and from n-type to p-type, vice versa. So owing to this, there is a diffusion process, and then this diffusion process results in the carriers which are majority in one piece of semiconductor to become minority in other, and then they recombine, and then you have the stable equilibrium back. Okay, so this is how that due to the application of external bias in the forward bias, you have the diffusion current, okay, across the p-n junction. So that's all for the forward bias. Remember that the forward bias is when the p-type semiconductor is connected to the positive terminal of the battery, and the n-type is connected to the negative of the external bias. Okay, and this helps in reducing the net electric field in the space pre-charge region. And this is vice versa in reverse bias. If you have to reverse bias this junction, or increase the IE field, or widen the depletion width, as we discussed in the last video, you have to reverse the terminal. So reverse bias and forward bias has to do with the terminals of the battery. Negative has to be connected to the p-type region, and positive is connected to the n-type region. Okay, as we have discussed in the last video. So that's all about the forward bias junction. We're going to discuss formally a diode and the IV characteristics in the upcoming lecture videos. Okay, that's all.